All right, welcome back. We are jumping into the next lesson. This one is called Proving Lines Are Parallel. Continued. All right, so what we did in the last section was we knew if we were ending a proof with like L is parallel to M, we knew that we were going to end that proof with the converse of one of the theorems because we were trying to prove that lines are parallel. We're going to find a few different ways to prove lines are parallel in this lesson. The start thinking part should ease us into this. It says, you have a 1-inch wide and 6-foot long piece of lumber. You're trying to create a line with a piece of chalk that is 8 inches away from a wall so that the line is parallel to the wall. Describe how you could do this. Now, what could you do? You have a piece of lumber, certain length long, doesn't really matter. It says it's 6 feet, but whatever. We need to make a line that is 8 inches from the wall and is parallel to the wall. How could we do that? Well, think about this. What about if we went over and put the board up against the wall and drew a line? And then we picked up the board and put it over here and drew the line. Since our board is only 1 inch wide, we could do that 8 times, and after 8 times, we would end up having a line that is 8 inches away. We'd also end up with a line that was parallel to the wall. Why is that? Well, this is the concept. If we had A and we made a line B that was parallel to A, and then we went over and made a line C that was parallel to B, and then we made another line ABCD which was parallel to C, what are you noticing is the relationship between A and D? Look at those. They are still parallel, and that is this. The transitive property of parallel lines just states if A is parallel to B and B is parallel to C, then A is parallel to C. Here is your example. All right, now 90% of the time when you're doing proofs, you are going to use this. So this is just kind of a side note. You'll use it on a select few proofs, but not many. But this is another tool in our toolbox. Now, another thing that we have here is if two lines are perpendicular to the same line, then what do you know? If I went over and whited this out and I drew a line, and I made something that was perpendicular to it. Now let's say I made another line that's also perpendicular to it. What do you notice about these two lines? They must be parallel. If two lines are perpendicular to the same line, then they must be parallel. Once again, here's a little specialty tool that you might use on a few proofs, but 90% of your proofs that you are proving lines are parallel will be finished with the converse of one of the theorems. All right, let's take a look at this and figure out how we could do this proof. In a plane, R is perpendicular to T. R is perpendicular to T. And S is perpendicular to T. Prove that R is parallel to S. Well, if we were allowed to just use the theorem, we would say since they're both perpendicular to the same line, they must be parallel, and we would just write that out. It would be a one-step proof. But what we're doing here is we're trying to prove theorem 3.9. Remember, you don't have to memorize those numbers. That's just saying the 9th theorem in the 3rd chapter. Different book would have different things. Just remember the theorem without the numbers. So let's go ahead and figure out how we could do this. Well, if this one was perpendicular to that, then we know that's a right angle. If this was perpendicular to that, that's a right angle. What do we know about all right angles? All right angles are congruent. Is that something that we have in our toolbox? All right angles are congruent. No, it's not in there, but we can add it in. Let me go ahead and add it right now so that we remember. Number 18 would be all right angles are congruent. We learned this few chapters ago, and we were like, why would we ever need to know this? Well, this is why. If that's right and that's right, and we know they're congruent, what type of angles are these? This one and that one are corresponding. If we know corresponding angles are congruent, then what do we know? The lines are parallel. So let's go ahead and do this. R is perpendicular to T, and S is perpendicular to T. That's given. That means that angle 1 and angle 2 must be right. How do I know that? Definition of perpendicular. If lines are perpendicular, then you end up with right angles. Then, therefore, what do we know? Angle 1 must be congruent to angle 2 because all right angles are congruent. Now, I thought we were talking about this angle and this angle, but we're talking about this angle and this angle, but they're still corresponding angles. So I could finish my proof by saying R is parallel to S by the converse of the corresponding angles theorem. Now that we've done this proof, we can use the theorem. So anytime you see two lines that are perpendicular to the same line on a plane, then you can say those two lines are parallel. You can use that theorem. Or we can just write out what the theorem says. Two lines perpendicular to the same line must be parallel. All right, so look at this. It says a carpenter plans to install molding on the sides of the top of a doorway. The carpenter cuts the ends of the top of the pieces, one end of each side at 45 degrees as shown. Will the sides of the pieces of the molding be parallel? Well, if this is 45 and this is 45, together they make what? 90 degrees, which means they are perpendicular. If this is 45 and this is 45, together they make what? 90, means they're perpendicular. What do we know about two lines that are perpendicular to the same line? They must be parallel. The other justification could be if that's 90 and 90, and both 90 and 90 add to be 180, you could have justified this by the converse of the same side interior angles postulate. Why? Because you have same side interior angles that are supplementary, which means that you can use the converse of that. All right, I hope that makes sense. Let's go ahead and do some proofs. In the end, I am trying to prove that L is parallel to N. So my mind goes straight to, oh, let's use the converse of one of the theorems to finish my proof. I don't know if that's actually going to work or not. Let's look through this. If 1 is congruent to 2, let's just put out our ideas. This is ugly. This is not good notation. I'm just thinking. 1 is congruent to 2. Ooh, look at those. Angle 2 is congruent to angle 3 by that. And 3 and 4 are supplementary. 3 and 4 are sup. And what can we do here? We got some of this information we might not actually need. In proofs, you gather a bunch of stuff. It's like when I was doing that project I told you about. I grabbed a bunch of tools and I thought I would use them all, but maybe I grabbed a tool that I didn't need. So we might not need one of these. If 3 and 4 are supplementary, and those are same side interior angles, then we know these are parallel. Why? Converse of SSIA. If you know 1 and 2 are congruent, then you know this one and this one are parallel by the converse of AIA. So it seems like we would be able to then show that L is parallel to N by the transitive property of parallel lines. Do I even need this? Does that help me at all? Nope. Just, it was cool that it was there, but it didn't help us with the proof. So let's go ahead and write out a proof. I want it to flow nicely. I'm going to make N parallel to M, then I'm going to show M is parallel to L, and then I'll be able to show Or let's go the other way. L is parallel to M is parallel to N, and then I can finish up with L is parallel to N. So let's deal with these two. Let's state angle 1 is congruent to angle 2. How do I know that? Given. Therefore, line L is parallel to line M by the converse of, that's alternate interior angles theorem, right? Next, I can say angle 3 and angle 4 are sup, which is just given. Therefore, line M must be parallel to line N by the converse. Sorry if you can't read that, that says given. Tried to write a little bit neater. It's just my stylus is not the best. That's the converse of SSIA postulate. And I can finish it up by line L is parallel to line N. And that would be the transitive property, of parallel lines. Okay, let's keep on going. Once again, 9 out of 10 times you're not going to use that. The next one says, in a plane, if a line is perpendicular to one of two parallel lines, then what? I don't know, let's draw it. Here are parallel lines. If something, a transversal or just a line, is perpendicular to one of the lines, what do you notice the relationship is to the other one? It is perpendicular to the other. The other. Okay, example of why it has to be in a plane. If a line is perpendicular to one of two parallel lines, let's go ahead and skip that part right there. It's just way too hard for me to draw the 3 dimensions to show why it could be a problem and why it needs to be a plane. Sorry. Let's just move on to the next one. Okay. We have this last page and then we are done. So, short, quick, easy lesson. This one says in a plane, A is perpendicular to B. Cool. Let's see. B is perpendicular to C. So you have two lines that are perpendicular to the same line in a plane. And then we know that C is parallel to D. And we want to show that A is parallel to D. Well, is there any way to show that A is parallel to C? Is there any way to show that that one is parallel to that one? Well, we have two lines that are perpendicular to the same line, so they must be parallel. Yeah. And then it's given that C is parallel to D. So then the transitive property will help me show that that's parallel to that one. Statement, reasons. On a plane, A is perpendicular to B and B is perpendicular to C. 3 points given. Therefore, A is parallel to C. And I don't know what the theorem, which one it was, so I don't remember the name of it. You can just write it out. Two lines perpendicular to the same line must be parallel. That's fine. We also know that C is parallel to D because that's given. And then I can just say A must be parallel to D because of the transitive property of parallel lines. Awesome. So it's a thought process. You kind of have to just sit there and come up with a plan of trying to figure out what you're going to do. Um, you don't want to just start writing the proof out, not knowing where it's going to go, because you're going to end up having to erase a million times. It's better to know what your proof is before you start writing. Okay, let's take a look at this last proof. It says NP is going to be perpendicular to NO. We also know that NP is perpendicular to PQ. Therefore, I know that those are going to be parallel. We also know that PQS, we know that this angle and this angle over here are supplementary. What type of angles are those? SSIA. Knowing that they're supplementary, does that help us? It does. It shows that these are going to be parallel. And then we can use the transitive property. Okay. Statements and reasons. First thing I'm going to connect is this one and that one. So I could say NP is perpendicular to NO, and NP is perpendicular to PQ. That's just given. Therefore, I know NO is going to be parallel to PQ. And that is two lines perpendicular to same line must be parallel. Then I know this stuff. I am going to write it out. Angle PQS and angle QSR are sup. Given. Therefore, now I can say those other ones are parallel. PQ is parallel to RS, and that is by converse of SSIA postulate. If you wrote theorem, I wouldn't take off. And then lastly, we can now use the transitive property. NO is parallel to RS by transitive property. Parallel lines. Okay. Now, just a little reminder, you should be keeping up on your geometry toolbox. Here's the toolbox. Know that 90% of the time when you are trying to prove that lines are parallel, you are going to be using the converse of one of these things. If you know the lines are parallel, 90% of the time you're going to be using one of these. Only about 5% of the time or 10% of the time you will use 16 or 17, meaning the transitive property of parallel lines or two lines perpendicular to the same line are parallel. And remember, that has to be on a plane. All right, I hope that made sense to you. And come to office hours with questions if you have any. Thanks for watching.